Welcome to this session of Materials Engineering. Myself, Nirvan Sarkar, Assistant Professor, Department of Mechanical Engineering of JIS College of Engineering, Kollam. Today's session, we will discuss about engineering and true stress strain, elastic and plastic deformation. So we are in module 2, that is in mechanical properties of material. And today's subtopic is engineering and true stress strain diagram, elastics and plastics deformation. Learning outcome: to understand the relation between engineering and true stress strain curve and plastic deformation. So first of all, we need to know what is engineering stress and engineering strain. During load extension, it is assumed that the dimensions of sample do not change during testing. In fact, during testing of a sample, its length increases and cross-section area decreases. But still, as a matter of convenience, it is assumed that they remain unchanged. So, by this method, if we found that it is found that the original cross-sectional area will remain same during loading up to breaking. So here the engineering stress is termed as sigma E, that is applied load by original cross-sectional area, and engineering strain E equal to change in length by original length. Next is what is true stress and true strain. As the tensile test proceeds, the length of the sample increases and correspondingly the area of the sample decreases. The value of true stress gradually increases because of continuous decreases in cross-sectional area, and true strain decreases due to continuous increase in length. So here we found that in actual cases, that is true strain, that is the instantaneous load by actual cross-sectional area at that instant. So true strain equal to, it is the summation of all engineering strain from instant to instant, and therefore E equal to given that L1 minus L0 by L0, where L0 is the initial length and L1 is then at instantaneous load at first point, the instantaneous length that is taken, plus L2 minus L1 by L1 plus L3 minus L2 by L2 and so on. So it may be said that summation of L0 to Li del L by L. So we can find it, that is ln of ultimately Li by L0, where 0, 1, 2, 3 are the instants at which the change in length is considered, and I is the last instant after which true strain is to be calculated. Now we assume that volume of the sample during the tensile testing will remain constant. So as we get, that is V is equal to A0 L0, that is equal to EI into Li. So therefore with this, the relation Li to L0 we may write A0 by AI. So now strain becomes ln of A0 by AI. Now, the relationship between engineering and true stress strain. True stress is equal to instantaneous load by actual cross-sectional area at that instant. That is P by EI. Now, we may rewrite this equation as P by A0, that is the original cross-sectional area, multiply into A0 by AI. So we can again rewrite P by A0 into Li by L0 from the relation. Where Li is the length of the sample at the instant I, and Li equal to original length plus change in length observed up to the instant I. That is L0 plus del L. Therefore, sigma T, that is the true stress, equal to sigma E into L0 by del L by L0. Again, we can write sigma E equal sigma E multiplied into 1 plus del L by L0. Now we know that is del L by L0 is the engineering strain. So therefore, the true stress sigma T, we can write sigma E, that is the engineering stress, multiply into 1 plus engineering strain, that is 1 plus E. So the equation, the relation between engineering stress and engineering strain with the true stress and true strain. So it becomes that true stress sigma T equal to sigma E into 1 plus E, where sigma T is the true stress, sigma E equal to the engineering stress, and E equal to engineering strain. Now again, engineering strain, that E we know that equal to ln by Li by L0. But again, Li, that is length of instantaneous, we may write L0, that is original length, plus del L, that is change in length observed up to the instant I. So therefore, E we can write ln of L0 plus del L by L0, which is again we can write ln of 1 plus E. So again, therefore, we can write, that is engineering strain E equal to ln of 1 plus E, that is engineering strain, that is which is equal to true strain here, that is equal to ln plus 1 plus E, that is the engineering strain. So here is a problem that we need to be solved. Is given that tensile test was conducted on a mild steel specimen of diameter 12.5 millimeter and gauge length of 50 millimeter. The loads at lower and upper yield points were 4500 kg and 4600 kg respectively. The minimum and fracture loads were 7500 kg and 5000 kg respectively. The gauge lengths are fracture was 62.5 millimeter. The diameter of the fracture place was found to be 8 millimeter. At a load of 2000 kg, the total extension was 0.035 millimeter. Determine the following, that is lower yield stress, upper yield stress, ultimate tensile stress, that is UTS, fracture stress, true fracture stress, percentage of elongation, percentage reduction in cross-sectional area, and Young modulus modulus of resilience, and last of all, modulus of toughness. So how to solution? That is, we know that lower yield stress, that is the lower yield load by original cross sectional area. So thus we find that lower yield load is 4500 and original cross sectional area, that is the diameter of the original cross section is 12.5 millimeter. So we need to convert it into the area, that is pi by 4 into d square, that is pi by 4 into 12.5 square. So thus we get that lower yield stress is equal to 36.7 kg per millimeter. Now the in second case, that is upper yield stress, that is equal to the upper yield load divided by original cross sectional area. So here it is given that upper yield load is 4600 kg divided by original cross sectional area, that is remain same, that is pi by 4 into 12.5 square. So thus we get upper yield stress equal to 37.5 kg per millimeter square. UTS, that is ultimate tensile strength, that is given ultimate tensile load by original cross sectional area. Ultimate tensile load for this problem given 7500 kg and its original cross sectional area remains same, that is pi by 4 into 12.5 square, that is will give 61.1 kg per millimeter square. Fracture stress, that is the fracture load by original cross sectional area, that is 5000 divided by pi by 4 12.5 square, that is 40.7 kg per millimeter square. So these are all from the engineering stress. Now while to calculate the true fracture stress, that is the true fracture load by area of cross section at fracture. So area of cross section, that is diameter of the after fracture, it is found to be 8 millimeter. So the true fracture stress we can calculate, that is from the by dividing between true fracture load divided by area of cross section at fracture. So the fracture load will remain same, that is 1500 kg divided by area of cross section at fracture, that is given by pi by 4 into 8 square. So that is 99.5 kg per millimeter square. Next, number 6, that is given percentage of elongation. So percentage of elongation is given final length minus original length by original length into 100. So that is final length is here given after the fracture, that is it is found to be 62.5 millimeter and original length that was 50.0 millimeter. So thus we get that percentage of elongation after calculation we find that is 25%. Percentage reduction in cross sectional area, that is original area minus final area by original area multiply into 100. So originally the diameter was, that is 12.5 millimeter, and finally the diameter was at fracture, after fracture it is found 8 millimeter. So the original area is pi by 4 12.5 whole square minus pi by 4 into 8 square divided by original area. So thus if we can calculate, so it is found that is percentage reduction in cross sectional area is 59%. Now next is Young modulus. So Young modulus is given, that is sigma T, that is by E, that is E is the strain. Sigma T is the true stress. So true stress, from the relation of true stress with engineering stress and strain, that is found to be, that is true stress is given, that is sigma E into 1 plus E, that is engineering strain, and true strain E is given ln of 1 plus E. So by replacing this sigma T and E, that is true stress and true strain, with the relation with engineering stress and engineering strain, thus we found this equation, that is Young modulus E is equal to sigma E 1 plus E by divided by ln of 1 plus E. Now at a load of 2000 kg, it is found that sigma E equal to 2000 by original cross sectional area, that is 16.297 kg per millimeter square, and E, that is engineering strain, here it is found that extension was 0.035, and with the original length of that bar, that was 50 millimeter. So thus we can calculate the engineering strain, that is 0.035 divided by 50, which is equal to 7 into 10 to the power minus 4. So therefore now we can calculate that Young modulus E equal to, by replacing all of these, that is sigma E and the value of E in the above equation. So thus we get that Young modulus equal to 2.331 into 10 to the power 4 kg per millimeter square. Now next is modulus of resilience. Modulus of resilience is denoted by, that is sigma y square by 2E. Sigma y, that is the upper yield load, divided by 2E, that is 2 into multiply into Young modulus. So at upper yield load, we have earlier calculated that value is 37.5 kg per millimeter square. So thus we are putting in this equation an E value just we calculated, that is 2.331 into 10 to the power 4. So thus we get modulus of resilience, that is up to elastic limit, that is 0.03 kg per mm square. Now after that, modulus of toughness, which is given by 2/3 of sigma U into EF. That is sigma U here ultimate tensile strength, and EF is equal to the strain at fracture. So thus we know that sigma U, that is ultimate tensile strength, we have calculated, that is 61.1, and strain at fracture, that is equal to 0.25. So thus we get modulus of toughness equal to 19.18 kg per mm square. Or this modulus of toughness we can calculate in another way. That equation is sigma y plus sigma u by 2 into EF. So it is more corrected, the second equation. So sigma y value we know, that is that lower yield point, that is 36.7, plus sigma u, that is UTS ultimate tensile strength 61.1 kg per mm square, divided by 2 into multiply into EF, that is that elongation at fracture. So thus we get that value is here, corrected value is 12.22 kg per mm square. Now in another problem is given, a tensile test was conducted on a mild steel. The following data was obtained from the test. Diameter of the steel bar equal to 3 centimeter, gauge length of the bar 20 centimeter, load at elastic limit equal to 250 kilonewton, extension at a load of 150 kilonewton equal to given 0.21 millimeter, maximum load 380 kilonewton, total extension is 60 millimeter. Diameter of the rod at the failure, it is found to be 2.25 centimeter. Now we need to be determined, that is Young modulus, number A, number B, the elastic limit, number C, the percentage elongation, and number D, the percentage decrease in area. So solution, first of all, we need to find the area of the rod A, which has the relation that is pi by 4 d square, and we get this one in terms of meter square, that is equal to 7.0685 into 10 to the power minus 4 meter square. So first of all, to find the Young modulus, first of all. So first, calculate the value of stress and strain within elastic limit. The load at elastic limit is given, but the extension corresponding to the load of elastic limit is not given. But a load of 150 kilonewton, which is within the elastic limit, and corresponding extension of 0.21 millimeter are given in the problem. Hence, these values are used for stress and stress strain with elastic limit. So the stress we know, that is resistance load, that is load by resistance area, that is equal to the resistance force by area, that is 150, which is equal to the load applied, that is 150 kilonewton converted into Newton, that is multiplied into 10 to the power 3 and divided by the area, that is we found in meter square. So it is found that stress equal to 21220.9 into 10 to the power 4 Newton per meter square, and strain equal to increase in length or extension by original length or gauge length. So increase in length, here it is given 0.21 millimeter, and original length is 20 centimeter. So it is now multiply into 10, that is 200 millimeter, which is equal to 0.00105. Now E, that is Young modulus, equal to stress by strain. So by putting the stress and strain value, we will get that 202.095 into 10 to the power 9 Newton per meter square, or which is given in, that is in giganewton, that is 202.095 giganewton per meter square. Now number B, that is the stress at the elastic limit is given by, that is to load at elastic limit by its area. So load at elastic limit is given 250 kilonewton, that is we are converting into Newton, and the area. So ultimately at elastic limit, the stress is, we found 353.68 meganewton per meter square. Next is the percentage decreased in length, that is obtained by, that is total increase in length by original length. So that is equal to given 60 by 200 into multiply into 100, that is 30%. Now last of all, the percentage decrease in area, that is original area minus area at the failure by original area, multiply into 100. So if we put all the value, so you will get here that percentage decrease in area is obtained, that is 43.75%. Now next is elastic deformation and plastic deformation. Elastic deformation, as we know, is reversible, that is recoverable. So if a material is loaded up to its elastic limit, and if we remove the load from that instant or within that zone, so materials is spring back to its original position due to its elasticity. So up to a certain limit of applied stress, strain experienced by the material will be the kind of recoverable, that is elastic in nature. This elastic strain is proportional to the stress applied. The proportional relation between the stress and elastic strain is given by the Hooke's law, which can be rewritten as, that is sigma equal to E, sigma by E equal to capital E, where sigma is the stress, small e is the strain, and capital E is the Young modulus. So E is termed as modulus of elasticity or Young modulus. Though Hooke's law is applicable to most of the engineering materials up to the elastic limits defined by the critical value of stress beyond which plastic deformation occurs. Some materials would not obey the law, example rubber. It has nonlinear stress-strain relationship and still satisfy the definition of an elastic material. For materials without linear elastic proportion, either tangent module or secant module is used in design calculation. The tangent module is taken as the slope of engineering stress strain curve at some specified level, while secant module represents the slope of secant drawn from the origin to some given point of the stress strain curve, as shown in next figure. That is, so in this figure it is shown that tangent and secant module of the nonlinear stress strain relationship. So if one dimension of the material changes, the dimensions of the material need to be changed to keep the volume constant. This lateral or transverse strain is related to the applied longitudinal strain by empirical means, and the ratio of transverse strain to longitudinal strain is known as Poisson's ratio. Transverse strain can be expected to be opposite in nature to longitudinal strain, and both longitudinal and transverse strains are linear strains. For most materials, the value of mu are close to 0.3. For polymer, it is between 0.4 to 0.5. For an ionic solid, it is around to 0.2. Stresses applied on material can be two kinds, that is normal stress and shear stress. Normal stresses causes linear strains, while shear stress causes shear strain. If the material is subjected to torsion, it results in torsional strain. Different stresses and corresponding strains are shown in the next figure. So here it is the schematic description of different kind of deformation and strain. So first of all, in this in case that is given, that is linear strain, where to equal and opposite force, pull force is applied and the strain is experienced, that is linear strain, while increasing in diameter and increasing in length and decreasing in diameter. And in the torsional strain, it is found that is two equal and opposite force are applied on two but two mutually different plane. So in this case, the body is tend to slides about its own plane, that is termed as produces torsional strain. So analogous to the relationship between normal stress and linear strain defined earlier, that is shear stress and shear strain in elastic range are related to as follows, that is tau is equal to capital G into sigma, gamma, where G is known as shear module of the material. It is also known as modulus of elasticity in shear. It is related to the Young modulus E, though through Poisson's ratio nu, as G, that is shear modulus of material, equal to E, that is Young modulus, by 2 into 1 plus nu, where nu is the Poisson's ratio. Similarly, the bulk modulus or volumetric modulus of elasticity K of a material is defined as the ratio of hydrostatic or mean stress to the volumetric strain, and the relationship between E and K is given by K bulk modulus equal to E by 3 into 1 minus 2 into nu. And let x, y, x, sigma x, y, and z are linear stresses, and the corresponding strain are in x, y, and z directions. Then we can found that mean stress equal to sigma x, sigma y plus sigma z by 3, and volumetric strain or cubical dilection is defined as the change in volume per unit volume. So that is del equal to 1 plus Ex, that is 1 plus Ey and 1 plus Ez minus 1, which is roughly equal to, that is Ex plus Ey and Ez. So we can get that volumetric strain equal to 3 into En, that is the mean strain. The Em is the mean strain or hydrostatic strain defined, that is Ex plus Ey plus Ez by 3, as shown in figure. All engineering material is usually subjected to stresses in multiple directions than in just one direction. If a cubic elements of material is subjected to normal stresses, that is sigma x, sigma y, and sigma z, strains in the corresponding directions is given by this equation. That is sigma Ex equal to 1 by E sigma x minus nu into sigma y plus sigma z, and correspondingly the sigma y and sigma z also. And the sigma x, the summation of sigma x, sigma y, and sigma z is given E by 1 minus 2 nu multiply into sigma x, sigma y, and sigma z. The strain equation can be modified, that is Ex equal to 1 by E sigma x minus nu into sigma y plus sigma z equal to 1 plus nu by E into sigma x minus nu by E multiply into sigma x, sigma y, and sigma z. After substituting the sum of stress into above equation, the stress can be related to strain as follows. That is sigma x equal to E by 1 plus nu into sigma x into Ex plus nu into E by 1 plus nu into 1 minus 2 nu and multiply into Ex, Ey, Ez. So ultimately we will get that in this equation can be rewritten as E by 1 plus nu sigma Ex into lambda into Ex, Y, and Z, which is lambda is known as Lamb's constant, that is lambda equal to mu into E divided by 1 plus nu multiplied into 1 minus 2 into mu. Using the above equations, it is possible to find strains from stresses and vice versa in elastic range. The basics of elastic deformation is formed by reversible displacement of atoms from their equilibrium position. On an atomic scale, elastic deformation can be viewed as a small change in the interatomic distance by stretching of interatomic bonds. That is, it involves small changes in interatomic distances. Elastic module measures the stiffness of the material. They are related to second derivative of the interatomic potential, or the first derivatives of the interatomic force versus interatomic distance. By examining these curves, we can tell which material has higher module. Elastic module can also be said as a measure of the resistance to separation of adjustment atoms and is proportional to the slope of the interatomic force versus interatomic distance curve. Hence, values of modules of elasticity are higher for ceramic material which consist of strong covalent and ionic bond. Elastic modules value are lower for metal when compared to ceramics and are even lower for polymer when one weak covalent bond is present. Moreover, since the interatomic force will strongly depend on the interatomic distances, as shown in next page, the elastic constant will vary with direction in the crystal lattice. That is, they are anisotropic in nature for a single crystal. However, as a small material consists of number of randomly oriented crystals, elastic constants of a material can be considered as isotropic. So here this figure is shown that variation of interatomic forces against the interatomic distances for both weak and strong interatomic bonds. The elastic modules are usually measured by direct measurement in tension or torsion test. For more precise measurement, dynamic techniques are employed. This test involves measurement of frequency of vibration or elapsed time for an ultrasonic pulse to travel down and back in the specimen. Because strain cycle occurs at very high rate, no time for heat transfer, and thus elastic constants are obtained under adiabatic conditions. Elastic modules obtained under isothermal and adiabatic conditions are related to this equation, which is equal to elastic adiabatic equal to elastic isothermal by 1 minus elastic isothermal T into alpha square by 9C, where alpha is the volume coefficient of thermal expansion and C is the specific heat. It can be observed that with the increased temperature, the module of elasticity diminishes. This is because intensity of thermal vibration of atom increases with temperature, which weakens the interatomic bonds. Now come to the plastic deformation. When the stress applied on a material exceeds its elastic limits, it imparts permanent, no recoverable deformation called plastic deformation in the material. Microscopically, it can be said of plastic deformation involves breaking of original atomic bonds, movement of atom, and the restoration of bonds. That is, plastic deformation is based on irreversible displacement of atom through substantial distances from their equilibrium position. The mechanisms of this deformation is different for crystalline and amorphous material. For crystalline material, deformation is accompanied by means of a process called slip that involves motion of dislocation. In amorphous material, plastic deformation takes place by viscous. So, in amorphous material, plastic deformation takes place by viscous flow mechanism in which atoms ion slides past one another under applied stress without any directionality. Plastic deformation is an as elastic deformation also characteristics by defining the relationship between stresses and the corresponding strains. However, the relation is not simpler as in case of elastic deformation, and in fact it is much more complex. It is because plastic deformation is accompanied by substantial movement of atomic planes, dislocations which can be encountered various obstacles. This movement becomes more complex as number slips system may get activated during the deformation. The analysis of plastic deformation and the large plastic strains involved is important in many manufacturing processes, especially forming processes. It is very difficult to describe the behavior of metals under complex conditions. Therefore, certain simplifying assumptions are usually necessary to obtain an amenable mathematical solution. Important assumptions thus involved in theory or plastically are neglecting the following aspects. First of all, an inelastic strain, which is time dependent recoverable strain. Number two, hysteresis behavior resulting from loading and unloading of material, and Bausch's effect. So Bausch's effect, that is depends on yield stresses on loading path and this direction. The relation described in the state of stress and strain are called consecutive equation because they depends on the material behavior. These relations are applicable to any material, whether it is elastic plastics or elastic plastic. Hooke's law, which states that strain is proportional to applied stress, is appreciable in elastic range where deformation is considered to be uniform. However, plastic deformation is indeed uniform, but only up to some extent of strain value. Where after plastic deformation is concentrated, the phenomena called necking. The change over from the uniform plastic deformation to no uniform plastic deformation is characteristic by ultimate tensile strength. As a result of complex mechanism involved in plastic deformation and its non-uniform distribution before material fracture, many functional relations have been proposed to quantify the stress-strain relation in plastic range. A true stress-strain relation plotted as curve is known as flow curve because it gives the stress required to cause the material to flow plastically to any extent of strain under a set of conditions. Other important parameters affecting the stress-strain curve are rate at which the load is applied and the temperature of the material. That is, stress is the function of strain, temperature and microstructure. So following are the most common equations that describes the material flow behavior. Sigma equal to k into e to the power n, where k is the strength coefficient and n is the strain hardening exponent. The strain hardening exponent may have values from n equal to 0 to 1. For most metals, N values are between 0.1 to 0.5. The power law equation described above is also known as Holloman loadings equation. Another kind of power equation which describes the material behavior when strain rate effects is prominent, where sigma equal to k into e to the e dot of m, where m is the index of strain rate sensitivity. If m equal to 0, the stress is independent of strain rate. M equal to 0.2 for common metals. If m equal to in between 0.4 to 0.9, the material may exhibit superplastic behavior, ability to deform by several 100% of strain without making. If m equal to 1, the material behaves like a viscous fluid and exhibits Newtonian flow. Deviation from the above power equation are frequently observed, especially at low strain or high strain. One common type of deviation is for a long log plot of power equation to result in two straight lines with different slopes. For data which do not follow the power equation, following equation could be used. That is sigma equal to k into E0 plus e to the power n, where E0 equal to the strain material had undergone before the present characterization. From the power law equation, the loadings equations, sigma equal to sigma 0 plus k into e to the power n, where sigma 0 is the yield strength of the material. Many other expressions for flow curve are available in literature. The true strain used in above equation should actually be the plastic strain value given by the following equation, where elastic strains can be safely neglected because plastic strains are very much when compared to the elastic strain value. So with this, we are likely to conclude this session. These are the references. Thank you for joining this session.